So before we begin today, I want to talk a little bit about our exam that we just completed. And I can send out this link afterwards. I know typing stuff in from URLs can be a little tricky. So exam, we ended up with a really wide spread of grades. So some people did well, but I know that for a bunch of you, probably this exam was a lot harder that you wanted, and you might not have performed the way you hoped or expected to. So I want to reassure you that there is still plenty of time in this class to affect your grades. We have plenty more assignments. This is not the end of the world, and this happens to some people every year. This is part of why this class is hard. It's just a shock. So what the form is, it has a whole list of things you could be doing to study, just to kind of jog your memory in case this is a study problem. I often feel about this exam that some part of it is the language of those questions. We do share questions between the different lecture sections, and some of them are based on the language in your textbook. So that can be sometimes a little confusing. So I'm going to be throwing in some more things phrased really formally in class so that we can practice that component. And the last thing about the exam, we're not going to pass those back to you, but what you can do is sit down either with me or with one of the TAs and go through individually the questions, see what you got wrong, kind of touch base on those topics, so that we're ready to move forward and we really make sure you get what went wrong and we can go on with that, especially if you're still struggling with any of that electrochemical stuff. Really important to make sure that we move forward with that, because it's gonna play a big role in our discussion of neurons, which is what we're moving to in unit 2. So this is just a reminder of my office hours, but you can also make an appointment with me outside of those. Available. You can also just come knock on my door, see if I'm there if it's not open. And I'm right upstairs above it. So any questions overall before we move forward with our content? So today we are going to be talking about osmosis, and in combing through your exams, I'm sorry I wrote this exam before we actually finished lecture, so I know there was one question on this. You guys all got points for that. You may have seen your grades shift around, by which I mean go up a little bit after class. So I did take into account that some of these questions I shouldn't have expected you to get right. So hopefully we've all heard the word osmosis before, right? Osmosis is the diffusion of water through a membrane, and it's able to diffuse through a membrane because membranes are semi-permeable, and when we're not given any other information about membranes, we should assume that they have aquaporins in them that are able to get water across. So basically that's our baseline assumption about membranes. We'll really only see one exception there when we start to actually talk about where the aquaporins come from and why when we get to kidney stuff and A&P. So just assume water can get through membranes. So osmosis is always going to be passive. Those aquaporins aren't pumping water. We're not moving water using energy. Water is always flowing down its own gradient. And where osmosis can sometimes get mentally tricky here is that often instead of having the water gradient labeled, we'll see a solute gradient labeled. You're going to have to flip those things in your head. Think about the water rather than the solute, and we'll go through what that looks like today. The other thing to note that water, while it's a polar molecule, it's not charged. So it's not like our ions. We don't have to worry about electrical driving forces. It doesn't have a charge, so it can be unaffected by any changes to membrane potential. So what we can see in this image is an explanation of our water gradient. Okay. So our water It's flowing in basically. On a conceptual level, I sometimes think about it as water flowing in to water down the solute. And I think about it that way because we're often given solute concentrations rather than water concentrations. So what you see here is our blue dots in this top image are telling us our solute concentration. And in fact, we have the number exactly right here. Okay. So this top example is telling us what would happen if we had a solute concentration of 0.3 moles, which is equivalent to 300 milliosmoles. We'll be talking about moles and osmoles a lot today, but basically, remember our units to get from moles to milliosmoles, you're going to multiply by 1,000. Okay. So if we have a solute concentration of 300 milliosmoles in the cell, and a and a solute concentration of 0 moles outside the cell. And I should say these are real concentrations that you might expect to see in real life. That is the typical solute concentration inside a cell, 300 milliosmoles. And this is what the situation would look like if you put a cell in pure water, which you might do in a lab somewhere, right? So in this case, we have more water, higher water concentration outside the cell. So we see that labeled in the second row. So here's our water concentration, 55.5 moles versus 55.2 moles. So we'll note that that higher solute concentration means we have a lower water concentration, right? 55.2 is less than 55.5. So we have our water flowing in. So that's the basic thing that we're going to be seeing throughout osmosis. Water flowing down its own gradient towards areas of higher solute concentration. We can see a different example below. So here we see that we have a solute concentration of 300 milliosmoles inside our cell, a typical cell, typical sort of baseline concentration. But now we have a solute concentration of 1,000 milliosmoles outside the cell, so much higher. And this image even tells us what that's from. It's from 1 molar sucrose. So we would multiply 1 times 1,000 to get that 1,000 milliosmoles. And we can see the effects that this has on the water concentration. So because we have all that sucrose outside the cell now, we compare this image versus this image, right? Our water concentration is now 54.5, when before in pure water we had it at 55.5. I wouldn't be asking you to calculate the water concentration, but we will be calculating solute concentrations, and we'll have a different slide on that. Okay. I'm just kind of previewing it before we have it in words. So the water concentration here is the same as it was before because our solute concentration inside the cell hasn't changed. So here we see the water flowing out towards that area of higher solute concentration, which means we have a lower water concentration. So this is what is happening when we're thinking about osmosis. So we refer to the total solute concentration of a solution as its osmolarity. And I want to be careful here when we say total. This really means everything. So we're going to see another word, tonicity, in a couple of minutes. That means something very slightly different. So here we mean the total solute concentration of absolutely everything that is in that water. So the reason that a higher solute concentration means a lower water concentration. Fundamentally about space, right? Hard to see it, right? But we have a limited amount of space inside a cell. We have a limited amount of space in, say a liter, right? So if we put more solutes in there, they take up some space, meaning they push water around, right? They displace the water. There's not as much room for water there. Even though if we're looking at it, say in our kitchen, right, we don't notice a difference in how much water it looks like there is in a pot when we put some salt in. But on the level of a cell, right, that space does matter. Right, so these are kind of like inverse of each other. If we have more solute, it means there's less room for water. So here's where we get to those calculations of moles versus osmoles. So both of these are still talking about osmolarity. This is just showing us how we would calculate. So a milliosmol is 1/1000th of an osmol. So we're going to multiply by 1,000 when we want to go the opposite way from moles to milliosmoles. Very simply, 0.1 moles of glucose are 0.1 osmoles if we put them in a liter of water. So that part is basic, it's easy. But what you'll notice is on that line below, right, we see that 0.1 moles of sodium chloride is 0.2 osmoles of a liter of water. So we have a difference here. Has anybody read ahead or remember from your homework assignment why that might be? Why do we have a difference here when we're looking at a salt, sodium chloride versus glucose? What happens to things that are ionically bonded in water? Anybody remember that from chemistry? I will show you. Yeah, exactly. So they separate in water, technical term being dissociate. Right? So if we drop table salt in water, we get two different ions, right? So that crystal form is dissolving. And now we get sodium ions and chloride ions. So our cation, the positive one, right? And our anion, the negative one. So the reason we're going from 0.1 moles to 0.2 osmoles is that when we dump in that sodium chloride, it's like we're dumping in both sodium ions and chloride ions. So when they separate, they're going to take up really twice as much space as a glucose molecule that stays together. Glucose doesn't break up when you put it in water. We know that we have to go through all of metabolism to break down glucose. So every time we see a salt or something ionically bonded, we want to remember to double that number to get the osmol. So here we saw, so the usual osmolarity in our cell is that number we saw in the previous example, about 300 milliosmoles. So before we do a couple practice questions here. Oh, sorry, yeah, go ahead.
So we double, like, say it was NaCl2, would you have to like calculate that there would be double?
Yes.
So it's only double if it's just like a singular molecule, like it's a molecule.
We're really going to see mainly pretty much only NaCl is going to be relevant to our purposes in physiology. But however many ions you would get is what you should be thinking of. So if you had something that formed 3 ions, that would be the case. I can't off the top of my head think of an example where that would happen, right? Because NaCl2 just doesn't exist. So I'm trying to think of something in my mind where that would happen, and I'm sure that there is something, but
Like SO4.
so that wouldn't dissociate, I don't think. Yeah. So can anybody think of an example of something ionically bonded? Like
Well, I was just wondering. if you
MgF2, I think. Yeah. We're going to see examples with two, but yeah, if we had something
can
bigger, yeah.
for us, and double.
Mhm. Yeah, those are all our things that are relevant physiologically. Oh, and up because I was going to do something. All right, so if we put these 2 points together, all right, so practicing our math. So if we had a 0.1 molar glucose solution, that gets us to a 0.1 osmolar glucose solution. So in physiology, we're going to be talking about milliosmoles. So how many milliosmoles is 0.1 osmoles going to be? Yep. So we're multiplying by 1,000, right? So we had 0.1. So we go 1, 2, 3, and it's going to get us to 100. So let us practice. So sucrose is going to work like glucose. So how many milliosmoles would we get? We have 0.15 moles of sucrose in a liter of water. I'll give you another couple seconds to get your answers in. Great. Yeah, so when we multiply our point, we know that our 0.15 mole is 0.15 osmole, and we're going to multiply that by 1,000, which would give us 150 million osmoles. And now let's try an example. A salt. I'll tell you that potassium chloride is salt, ionically bound. So how many milliosmoles if we put the same amount of potassium chloride in water? And a couple more seconds. So yeah, just like sodium chloride, this would dissolve into two different ions. So we're going to get positive potassium ions or cations, or negative chloride ions or anions. We're going to have to double, therefore. So 0.5 moles of potassium chloride would be 0.3 moles, or osmoles, in the water. Then we multiply that by 1,000 to get our milliosmoles. So finally, let's say we have both of these in water. What do we think would happen if we put both that 0.15 molar sucrose and that 0.15 molar potassium chloride into water? How many osmoles would we get? Okay, seconds. So the correct answer is 450. So what we did here, right? We know that the sucrose was 0.1, text button, right? Sucrose. We had our 0.15 moles goes to 0.15 osmoles times 1,000 to get us to the milliosmoles. So we had 150 milliosmoles. Then our potassium chloride separates. So we had 0.15 moles. We're going to have to multiply by 2 because we're forming those two ions, which means we have 0.3 osmoles, which we then multiply by 1,000, giving us the 300 milliosmoles from the previous question. And these things are additive. So when we talk about osmolarity, we're going to add together everything that is dissolved in that water. Right? We're not looking at a specific ion or a specific molecule, we're looking at all of it. So we're going to add the osmolarity of the sucrose to the osmolarity of our potassium chloride, giving us our 450 milliosmoles. We should be able to do problems similar like this to this, and also therefore compare after calculating out, say we have information about what's dissolved inside the cell versus outside the cell, we should be able to tell which has greater osmolarity, which ultimately will tell us about which way the water flows. The questions about these calculations before we move forward. When we talk about osmolarity, and eventually when we talk about punicity next, we're going to see these terms isoosmotic, hyperosmotic, and hypoosmotic. So they refer to things that have the same osmolarity, so isoosmotic means same osmolarity. Hyperosmotic, going to mean more, greater osmolarity. The hypoosmotic is going to mean lesser, lower osmolarity. So this is going to have an effect on what happens to our flow of water, right? So in this image, we can imagine, based on the titles, what's going on with the solutes, right? So here we have an example of a hyperosmotic solution, a cell in a hyperosmotic solution. So we should be imagining, hyper means greater, means a lot. So we should be imagining lots of solute out here and not very much in the cell. Okay. So the water is traveling towards that greater, that hyperosmotic solution, moving out. In an isoosmotic solution, iso meaning same, absent any other information, we wouldn't expect water to move. When we talk about tonicity, if we have information about the tonicity, we might need to change that assumption. So if we see iso, means the same, probably not going to move. In a hypoosmotic solution, we have the opposite situation to our hyperosmotic. So we're going to have a lot of solute inside our cell. Maybe we have pure water outside, right? Maybe we don't have any solute at all. So the water would travel in to the cell. And this might actually have the effect of bursting the cell. So lysis means bursting or breaking, right? So we might expect a cell at a certain point, if water keeps flowing in and in and in, because there's stuff in a cell. If we're in pure water, this is going to keep happening. We would expect that cell to get so big that the membrane can't contain all that water inside anymore. It could burst. The opposite thing is happening in the hyperosmotic solution. You'll notice started to shrivel. Right? We technically call that crenated because these are like crenations, kind of like crannies in an English muffin. Another way we will talk about osmosis by talking about something called the osmotic pressure. So the osmotic pressure is an indirect measure of our solute concentration. So we're not going to measure it in osmoles or milliosmoles. We're going to measure it in a unit of pressure. So here you see ATM, right? So atmospheres is our measurement for our osmotic pressure. The way we can think about osmotic pressure is the ability to like kind of pull on water. So we'll note here where we have these labels, where we have higher solute concentration, we also have higher osmotic pressure. So if you see a high osmotic pressure, you should know that that means there's lots of solute there. Technically, the reason we have a higher osmotic pressure with a higher solute concentration, but if we were trying to like physically measure the osmotic pressure, we're actually measuring like how much pressure we would need to apply to kind of push against that water flow to actually stop the movement of water. But we can think about it as a pull. But that makes sense, right? So we have these solutes pulling, that high osmotic pressure is pulling on it, but we have to push against that pull if we wanted to stop it. So here in the image, I can compare, right? We have our solute concentration is lower on side 1 and higher on side 2, which means the same thing is true for our osmotic pressure. lower on side 1, higher on side 2, which means the inverse is true for our water concentration. So here, where we had a solute concentration of 300, we now have our water concentration of 55.2, so it's higher. Then on side 2, it's a little bit lower. So water is flowing down its own gradient. It's the opposite of the solute concentration or the osmotic pressure gradient. So we would say that water flows against a solute gradient, or water flows against an osmotic pressure gradient. We could calculate that gradient as well for osmotic pressure. You take side 2, right, that's 12.3, subtract our 7.4, and we would see that we have a 4.9 atmosphere osmotic pressure gradient. And in the future, as we start to talk about like blood vessels, we will be talking about different pressures and their influence on how water travels across membranes. So these numbers and these types of calculations will come back in the future. But specifically, we're going to end up talking about pressures. We're going to remember osmotic pressure. And we'll see that pi indicates that it's an osmotic pressure. You don't have to remember that for now, but in the future, we'll be talking about multiple types of pressures. I'm just going to point it out now so that when I jog your memory later, you know what I'm talking about. At least vaguely remember that we looked at it once. So here's where we get to tonicity. So osmolarity was talking about all the solutes dissolved in the water. But when we talk about tonicity, we are going to think only about impermeant solutes. What do you think impermeant means? Impermeant. So we've seen that root before, the perm part, right? So what did we refer to as semi-permeable? What part of the cell? Yeah, exactly, the membrane. So the membrane was semi-permeable. So a solute that is impermeant is one that cannot cross the membrane. So impermeant solutes can't cross cell membrane. They're actually going to have a different kind of effect on water, more of an effect than our permeant solutes would. Because if we had a solute that could cross the membrane, we would expect that it might cross, right? Like instead of having water balance it out, we would expect that that permeant solute would be potentially traveling down its own gradient. So we'd have more of a shifting situation than we would if we're looking at an impermeant solute. We are usually looking at impermeant solutes, I should say. We are usually looking at things like ions, things like glucose. But for example, if we were thinking about gas, like oxygen dissolved in there, we would know that that could permeate, could move across the membrane through simple diffusion. So not every single molecule we see is going to be an impermeant solute. However, tonicity would have the same effect that we see on cell volume from that previous slide with our osmolarity. Right, so we can see that a low osmolarity, we'd have the cell growing, right, as water is moving in. So this would be hypotonic, right, meaning that the water would move in. Right, here we have our hypotonic solution. In the center, we'd have our isotonic solution, so we wouldn't expect to see movement. And then we have our hypertonic solution, right? So it's more. The reason we're always comparing it to that 300 is that is what we should expect our cells to be at. We don't have any other information. Okay? So in this case, the water moving in or the water moving out in the hypertonic solution. Yeah, that's why this cell is shrinking, our water is moving out. So here we see a slightly more complicated situation than when we were talking about just the osmolarity. So now we're comparing these concepts of osmolarity and tonicity. So one of these images, we have an isoosmotic solution, an isoosmotic situation, but it's not isotonic. So which is that, the left or the right? Okay, so isoosmotic, right? This is referring to our total concentration of solutes, right? So the total space that our molecules take up is the same in an isoosmotic one. So where do we see things evenly spread out across the membrane? Yeah, so the left, we have a roughly even spread, right? So this would be isoosmotic. We're going to ignore the color basically when we're talking about the osmolarity. So if we calculated the osmolarity, we wouldn't pay attention to whether it's our impermeant solute, say sodium ions or something, or if it's our permeant solute, which in this case is going to be a molecule called urea. Okay, so here's our isoosmotic part, but it's not isotonic because for tonicity, we are referring only to the impermeant solutes. So would we say that this cell is in a hyper or a hypotonic solution? Yeah. So here we have isoosmotic solution, but it's hypotonic because we're paying attention only to the purple stuff, right? So we should let the yellow fade into the background. We're not going to pay any attention to it because it can travel across that membrane, right? So it's going to start to even itself out, which means that it's not going to have as much of an effect on water because that gradient is going to start shifting. Okay, so that, yeah, go ahead.
I think your colors are throwing me off. So how did you figure out it was hypertonic?
Yeah, okay. So when we're looking at tonicity equals the impermeant solutes. So the purple ones. Okay. So where do we have a lot of purple dots? Yep. Okay, so high concentration. That means that our low concentration is where? Yep. So that's how we get that low tonicity, right? So that's how we get the hypotonic, is that concentration of the impermeant solute. Does that make sense?
Yeah, so if all the purple was on the outside, then it would be the hyper, and then if it was hypertonic, it would be purple on the inside.
Yeah. Does that make sense to everybody? what we see on the right side of the image is we have started to look at what would happen as we let everything just kind of progress naturally, right? So what we see happening is that the urea, this molecule that is permeable, right, can permeate solute. It has started to actively permeate the membrane. So what do we note about the spread of that urea across the membrane? Well, do we see a gradient for urea here? Might be hard to tell with all those dots, but what's happened here is that urea has moved to equilibrium, basically, right? You guys see that, how the yellow is kind of spread out, so it's about evenly spaced outside and inside the cell. But what about those purple dots? What about the impermanent solutes? Maybe sodium ions. No. Have they moved? No. No. Okay. So what does that do to our osmolarity inside the cell? Yeah. So when we're looking at the osmolarity, we're counting up the stuff. Osmolarity has to do with everything, right? So now we're counting up all those yellow dots and the purple dots. So we've raised the osmolarity above 300 because there's now more stuff in the cell. Okay. So if we wanted to talk about the osmolarity here on the right, what do we say? Hyper osmotic, iso-osmotic, or hyper. So did I do them in order? Are we going to pick hypo, iso, or hyper for the osmolarity of the solution here? Solution relative to cell. So now we're going to have a hypo osmotic solution, because just by the movement there of our solute that can permeate the membrane, right now we have 300 outside, more than 300 inside, so we're lower outside. And we have water flowing down the water gradient, therefore, which is about the space between the molecules here. So we're going to start watering down the inside of that cell. This is a little complex to think about, but that's the basic picture of what's going on here. Questions about this? Let's make sure. So let's pick the right word for the tonicity here as well. So are we hypotonic, isotonic, or hypertonic? Yep, we haven't changed the tonicity, or still have a hypotonic. So now a big long question. We're going to think about a membrane permeable to water, so just like we would expect when we're thinking about osmosis questions, separating chambers, so a tube or something, into A&P. Now think about what would happen if compartment A has a 15 millimolar solution, compartment B has a 60 millimolar solution. Both of these are non-permeating solutes. give it another couple seconds. Talk about it. So when we are thinking about these two chambers, right? So compartment A is relatively a low solute concentration or a high solute concentration here on side A. It's low, right? So here's our low side on side A. Here's our high side, therefore, on side B. So if these solutes could move, they would move from the 60 to the 15, but because they are non-permeating, by definition, that means they can't move. So now let's think about where there is more or less water, and I'll write that in blue. So which side contains a high water concentration, A or B? Yep. So here we have our higher water concentration, which means that this is our lower water concentration. So we're going to have movement from A to B, high to low, down that water concentration. So we think of it basically as the inverse. Yeah, so we're thinking about it just as physical space, right? So if we're taking up only a little bit of space with our solute, there's lots and lots of room for the water. Does that make sense? You can almost think of it like, I don't know if this helps at all, right? But like if you think about it like as a pie chart, right? Like if we have a little bit of solute, that means the rest is big. If we have a lot of solute, take out small. Does that make sense? Yeah. Okay. So yeah, so the answer would be that last one, moving from this high to this low. So we will stop here. So this is just a chart kind of defining what these terms would be physically and physiology. And this is just illustrating the effect it would have on cell body. We'll pick up here next time. And instead of going through the epithelia stuff that you have in your membrane-free packet, we're actually going to move straight into our next thing, talking about our neurons. So just so you know, if you're printing stuff out, be ready for that next time.